stop.
Why are those strings there anyway if they made that thing rigid?
The strings are there because this thing would like wobble super hard when the fans were on. So
And those strings are supposed to keep it stable?
I guess so. I don't know. I didn't put them on.
I mean, if it was a wired cable,
That could work,
but it's like what? Cotton string, nylon string?
yeah.
It probably stretched quite a bit. I don't think you're doing anything now. A little tight. But anyway, so what we're talking about is speeds and feeds. So chip load. What is chip load, guys? Don't read the definition. I mean, what is it?
It's
When you did this your homework, you had to find the chip load, right?
Ah.
To do the feed rate, correct? So what is the chip load usually? Oh man, you guys are slacking.
Yeah. Well, we had a week off, man. It's like,
That's alright, that's why we're reviewing. That's why we're reviewing. So chip load is how big of a bite each tooth takes, right? So if I got this cutter and it's got chip load of 1,000, that means each tooth is going to take off 1,000th of the material, right? So if I turn this, it's got 4 teeth. If I turn it one time, it's going to take off 4,000th total, right? Because based on the tooth. So basically, it tells you how hard the tool is working. So obviously, if I'm taking a 10,000th chip load with the same tool, it's going to be working a lot harder than 30,000th chip load unless your tool's huge. If you got a big tool, it's alright.
That's what she said.
Don't try to do that with a 1/8" cutter or something. You're gonna break it. That's more than. Yeah, that would mean like one revolution. Yeah, no, that's not gonna work. So the chip load varies between the size of the tool usually. So you'll see that a lot in the charts. If it's a smaller tool, it's gonna have a much smaller chip load. Like if I'm using a 30-seconds tool, I might not even use 1,000. It might even be a 1/2,000 chip load. But you got to remember that thing's spinning a lot faster too.
so you can cut a lot. The feed could be a lot faster with a smaller chip load.
No, the higher chip load means your feed goes up. Because what's the formula for feed rate?
I lost my paper in that computer lab.
feet per revolution?
No, feed inches per minute. It's the number of teeth, right? Number of teeth times the chip load times the speed, right? I don't know if it's in that order on whatever you're looking at, but that's usually what it is. So that means if my chip load increases, they're all multiplied, right? So that means my feed must increase.
So IPM is your
Inches per minute is your feed rate. That's how fast you're feeding into the material. Okay. We'll get to that. So surface feed per minute. What are we talking about here? What's the surface feed per minute? You guys remember where I was talking about the cars going down the highway?
See, I was not here for that one.
So if I'm driving in my car, right, I'm going 60 miles per hour. My wheels in my car are spinning, right?
Is your car shaking?
Usually going twice
No.
as fast.
No.
Say my wheels in my car are, I don't know, this big. There's the wheels in my car, right?
small
And I'm going 60 miles per hour, right? And right beside me is a big old semi-truck. It's got a huge wheel, right?
Well, that's like totally disproportional.
And he's going 60 miles per hour too.
It's like a.
But he's
And then
getting
I've
more
got-
surface. He's getting more surface feed.
No, he's getting the same service speed. We're going the same speed,
Oh,
right? And then I got this little smart car behind me. And it's this big, right? But it's still going 60 miles per hour, right? So this is what we're worried about. We're worried about how fast are you actually moving across the surface. So 60 miles per hour, that'd be what, 5,280 surface feet per minute? Which is ridiculous. You would never cut anything that fast, for sure. But what's that mean about the rotational speeds of these?
Unless you were cutting stuff on the highway with concrete.
What's the rotational speeds of these? They're all going to be rotating
No, because there's different radius.
So which one's gonna be going the fastest?
Small.
This one, right? This one's gonna be spinning real fast. Right? This one's gonna be going really slow, right? And your car's gonna be somewhere in the middle, right? So the service speed per minute is just telling us how fast is that tooth, that single tooth. Just think of one tooth moving across the surface, right? So think about it this way: if I move something really quick across the surface versus really slow, which is going to create more heat? Fast, right? So your surface speed controls your heat in your cutting, really. That's what you're talking about, is how much heat is there. So,
Going back to that first equation, what's LL for again?
we'll get to that. Don't worry about it. We'll get to that.
Okay.
So every cutter has a diameter, right? So that's our car wheels over there. We have 3 different diameters. And you multiply that by the circumference, you get the distance it travels. So we're talking about the rotational now. And the service speed per minute is just how far the cutter edge travels in 1 minute. So you're thinking about that cutter edge traveling a linear velocity in 1 minute. And that's what the service speed per minute is. And you'll see on the chart anywhere from 20 service speed per minute all the way up to 3,000 for some crazy materials. Yeah.
Are we taking a break anytime soon?
Yeah, after we finish this. Then you'll be the last time.
Sorry.
So, just remember to think about that as how fast one tooth is moving across the surface. Just think of it that way. It's easy to remember.
It's okay. So when it's on the lathe,
Yeah.
that tooth, it's actually dependent on how big the diameter is of whatever you're cutting.
Exactly.
Okay, so I kept thinking it has to do only with the tooth. That's why.
No, it has to do with whatever's rotating.
Okay.
Like that.
Fuck. That was scary. Thought the school was getting blown up.
So, what's service speed per minute? It's the speed that your tool is moving across the material. So if you were to think of it as like a chisel, like I just got a chisel and I'm chiseling something, if I take that chisel and go fast, or if I go slow, that's what your service speed is. So the faster you go, the more heat you have, right? The slower you go, you have a little less heat. So if you look at this sheet, this chart here, kind of hard to see, it's small, I get it, but
That would have been nice.
you have your service speed per minute right here. It's going from 10 all the way to 1200, 2000, right? So 10 to 2000, and across the top you have diameters. And what you see happening here is like at 10 service speed per minute, depending on the diameter, your cutting, your RPM's going to change, right? So if I'm using an 8-inch tool at 10 service speed per minute, it's going to be 305 rotations per minute, right? But if I go up to a 1-inch, it's only going to be 38. So the tool diameter has a lot to do with how fast you're spinning your tool.
So on the outside, it's not going to be going as fast as if it were on the inside, surface-wise.
Yeah.
Okay.
So that brings us to spindle speed, which is the RPM of your machine. So the RPM of the Bridgeport, the actual tool spinning, or the RPM of your lathe piece spinning towards you or away from you. And that is your service speed per minute times this constant. They spent millions of dollars trying to figure out what this constant is, and then you divide that by B.
And that's
Is that the 3.189?
Yeah, they just rounded 3.82.
That's how we got 700.
It's fine if you use
Yeah.
3.82. You're not going to be off by that much. Just don't use 3.8 because that 0.2 can make a pretty big
Yeah.
difference by some amount.
Hopefully. I was trying
At
to
least
read
got
into
number one right.
I was trying to read into that damn thing too hard. Too much, man.
So, let's do an example here. We want to cut some aluminum. And the cutting speed we looked up in the chart for our tool was 900 surface feet per minute. Okay? And let's say we're using a half-inch cutter, half-inch tool. So all you do, just plug it in. So 900 times 3.82 divided by 0.5. And that should give you your RPM. What is that?
$68.76.
6876.
That's all I got.
900 times 3.82 divided by 0.5. What'd you say?
68.76.
Oh, I thought you said 68,000 or something.
No.
Yeah, that's the same.
Yeah, so that means it needs to be spinning 6,800 roughly RPM, right? No machine in this class can do that.
We were just talking about hooking up a car to the lathe motor.
I've seen people do that actually.
Really?
Yeah, I've seen people I've seen it like down in Kentucky. Like people,
Only in Kentucky.
Only in Kentucky. But they'll take their lug nuts and they'll bolt on like pieces of wood. And
Wood?
Yeah, they'll make like art out of it. I've seen it. It's pretty crazy
So
stuff.
they just
Very
bolt
dangerous.
something to their wheel and turn the car on.
Yeah, basically they had their car on blocks, they took off their wheel, they bolted a piece of wood on there,
I'm gonna try that.
cranked
That's
that thing up
awesome.
with the gas, and they had like a bar in the ground, and it was like a lathe basically.
Yeah.
And they were like making bowls and lampshades and all kinds of stuff. So
With wood or?
with wood,
Yeah.
yeah. So here's our RPM right there. So that means I gotta run the Bridgeport at that fast if I want 900 surface feet per minute, right? Obviously, we're not cutting at 900 surface feet per minute back there. Not with a half-inch tool, at least, right? So let's upgrade this to let's say it's a 1.75. What's that going to come out to?
1964?
0.5.
Yeah. Wait.
Don't. We can't do the 0.5.
19,
We'll put it there, but
1965 then.
so you can see how much that dropped now. Huge amount. And that's because our tool got bigger. So that means the outside spinning,
It's slower.
yeah, the tool got bigger. So the outside, we want that to spin at the same speed, right? So that means we got to spin slower. And that's, what is that? That's a huge amount smaller.
So even if the whole thing, let's say, is
It's like a 26% or 7.
It's actually a factor of 3.5. It's 3.5 times smaller. So,
Or like 25% of the number. Well, yeah.
no, it'd be like
Factor.
350%. Right?
you
I'm
said
looking at
3.5.
I'm looking at it
Yeah.
backwards.
Yeah, it's 350%.
That's
So-
right. You're right.
If you're back on the Bridgeport and that thing only spins at 4,000 RPM, or not even that probably, it probably spins at 3 something, and you want to get a high service feet per minute, you should probably use a bigger tool, right? That'd be a quick and dirty way to do it. So, if I'm on the lathe, what's different about this?
Not the tool, but how big the piece of...
How big the piece of stock is, right?
Yeah.
So if I'm cutting something 1.75 inch, I'm good to go. I can run the lathe at that speed, no problem, right? And I'd be cutting 900 surface feet per minute.
So people actually measure this stuff out, they don't just throw it on there.
On a manual mill, most people just throw it on there and go. Because you don't really need to, you can feel it. You can hear it, you can see it, it's easy to adjust. Nobody really calculates, I mean, guys who are manual mills know this stuff by heart. I never calculated speed to feet per manual mill unless it was something really important. CNC though, it's crucial. You gotta be perfect. You gotta be like right on or your parts are gonna turn out like crap. So that's why this is important. Because we're gonna start doing CNC right after welding. So
What are we doing welding?
welding next week.
Cool.
So these are the only two variables you have here, the cutter diameter and the surface feet per minute.